Every map you have ever seen begins with a fundamental deception. It presents a world of fixed points of continents and cities locked in place. But this is an illusion, a convenient fiction we tell ourselves to navigate a reality that is in truth a cascade of unending motion. You feel still anchored by the familiar weight of your own body, yet in this very moment you're a passenger on an impossible journey. You're hurtling through the cosmos at a speed so immense it defies all terrestrial comparison, a velocity woven from a tapestry of movements, each one nested inside another like cosmic Russian dolls. Let us peel back these layers of motion one by one. Your first ride is the Earth itself, a colossal sphere of rock and iron spinning on its axis at over 1,000 miles per hour at the equator. This is the gentle daily waltz that gives us sunrise and sunset, a motion so constant, so reliable, we don't even feel the ground move. But this planetary pirouette is merely the opening act. Our world is simultaneously locked in a grand sweeping orbit, a year-long pilgrimage around our parent star, the Sun. We are careening through the vacuum at 67,000 miles per hour, a speed at which you could cross North America in just under 3 minutes. Each year we complete a celestial loop of nearly 600 million miles, never returning to the same point in space because our entire solar system is itself adrift on a far greater current. Our Sun, a fairly ordinary star in a quiet suburban spiral arm, is a member of an immense swirling metropolis of stars we call the Milky Way. And it is anything but stationary. It drags us its entire family of planets, moons, and asteroids on a vast, circuitous journey around the galactic core. This is a motion of truly astronomical scale. Our speed is a staggering 500,000 miles per hour. Even at this breathtaking pace, a single orbit one galactic year takes our solar system nearly 230 million Earth years to complete. The last time we were in this cosmic neighbourhood, dinosaurs were just beginning their reign, and the continents were fused into the supercontinent Pangaea. We are voyagers through stellar nurseries where new suns are being forged, drifting past the ghostly remnants of stars that died billions of years ago. This galactic tide pulls us onward, a relentless migration through time and space. For generations, this was the largest journey we could comprehend. Our galaxy, we thought, was our universe, a vast, majestic, but ultimately self-contained island of light. But in the early 20th century, our cosmic map was violently redrawn. We discovered that the faint, fuzzy nebulae in our telescopes were not clouds of gas within our own galaxy. They were other galaxies. Hundreds of billions of them, each a Milky Way in its own right, each containing billions of stars and trillions of worlds. And in that moment of profound revelation, we were faced with a new, more fundamental question. If everything is moving, what are we moving relative to? How can we chart our course if there is no fixed shore in this cosmic ocean? The answer arrived not as a flash of light, but as a faint, persistent whisper, a ghostly echo from the dawn of time itself. It is the cosmic microwave background, the afterglow of the Big Bang. This is the oldest light in the universe, a faint radiation that bathes everything everywhere in its ancient glow. And it provides us with the ultimate frame of reference. It is the closest thing we have to a state of absolute rest for the universe. By measuring our motion against this primordial light, we can finally calculate the true, unadulterated velocity of our home galaxy. We can finally know where the Milky Way is going. When astronomers first made this measurement, they found something astonishing. After subtracting the Earth's spin, its orbit, the solar system's journey, our entire galaxy, our local group of neighbouring galaxies, everything is being propelled through the universe at an incredible velocity. 1.3 million miles per hour, 630 kilometers per second. It is a speed that is difficult to wrap the human mind around. It is a velocity so extreme that something truly colossal must be responsible. And so began one of the greatest detective stories in the history of science, the search for the engine driving our galaxy across the universe. The prime suspect was, and for decades remained obvious, gravity. The grand architect of the cosmos, the force that binds planets to stars, stars to galaxies and galaxies into magnificent, sprawling superstructures. Newton's apple falls to the Earth falls around the Sun. The Sun falls toward the galactic centre. The cosmic rule seemed simple: elegant and universal matter pulls on matter. Our galaxy's extraordinary speed therefore must be the result of a pull. We must be falling towards something immense, something with a gravitational grip so powerful it could command the allegiance of 100,000 galaxies like our own. And so astronomers began to scan the heavens, not with their eyes, but with instruments that could map the invisible. They weren't looking for light, they were looking for mass. They were charting the gravitational topography of the local universe, searching for the cosmic equivalent of a massive mountain range, a great basin of space-time toward which everything was flowing. The search was complicated by our own galaxy. The dense plane of the Milky Way with its thick clouds of dust and gas creates a zone of obscuration, a frustrating blind spot that stretches across a huge portion of our sky, hiding whatever lies beyond. It was like trying to map a distant continent from a valley shrouded in fog. But painstakingly, galaxy by galaxy, survey by survey, a picture began to emerge. They found filaments and walls, gargantuan structures of galaxies strung together like luminous pearls on invisible cosmic threads. They mapped the Virgo Supercluster, our own home complex of galaxies, and saw that it too was part of this great migration. And they saw that all of these cosmic rivers, these streams of galaxies, seemed to be flowing in the same general direction, toward a single unseen and unimaginably massive concentration of matter. They called it the Great Attractor. For years it remained a theoretical ghost, a gravitational anomaly inferred from the synchronized dance of tens of thousands of galaxies. Its heart lay hidden squarely behind the zone of obscuration, its true nature a tantalizing mystery. As technology improved, we began to pierce that dusty veil. We developed techniques to see through the galactic smog using radio waves and infrared light to map the hidden universe. And we found it. Or rather, we found what we believed was its core. The Norma Cluster, a rich and ancient city of galaxies blazing with the light of old red stars, its collective mass exerting a staggering gravitational pull. This, we believed, was the primary engine of our cosmic motion. Our galaxy, the Milky Way, was simply one of many caught in the inexorable gravitational current, being pulled toward this cosmic drain 65 million light-years away. The story felt complete. It was a satisfying conclusion, a testament to the power of gravity to shape the universe on the grandest of scales. Our trajectory was set, our destination known. We were falling toward the Great Attractor. But science is a restless endeavour. Its truths are provisional, its conclusions constantly tested. And as our maps of the cosmos grew ever more detailed, ever more precise, a nagging discrepancy began to appear. A small but persistent anomaly that refused to go away. When astronomers meticulously added up the gravitational influence of all the known structures, the Virgo Supercluster, the Norma Cluster, the Great Attractor, and even more distant congregations of mass, they discovered something deeply unsettling. The numbers didn't quite add up. The combined pull of all this visible and dark matter could account for a large part of our motion, yes, but not all of it. There was a leftover velocity, a significant component of our speed, that pointed somewhere else entirely. It was as if we were in a river and we had accounted for the main current, but there was an additional, mysterious cross-current pushing us sideways, a force that had no visible source. This rogue vector, this peculiar velocity, was a ghost in the machine, a profound challenge to our understanding of cosmic dynamics. For decades, the simple, elegant model of gravity as a purely attractive force had served us well. Things pulled. The more massive the thing, the stronger the pull. That was the law. It built the universe we see around us. But what if the law was incomplete? What if the story wasn't just about the pull of cosmic giants? What if the empty spaces between them played an equally important but entirely opposite role? We are intuitively drawn to substance. We map the stars, the galaxies, the clusters. We chart the things that are there. But the universe is defined as much by its absences as its presences. Between the filaments and walls of the cosmic web lie voids of staggering emptiness. Vast, dark, cold regions, some hundreds of millions of light-years across, where galaxies are hauntingly scarce. We had always treated these voids as passive, as simply the empty stage upon which the grand cosmic drama of gravity unfolded. But what if they were active participants? What if an immense region of profound underdensity, A cosmic desert could exert a force not of attraction but of repulsion. What if, in addition to being pulled from the front, our galaxy was also being pushed from behind? This was a revolutionary, almost heretical idea. It ran counter to our fundamental intuition about how gravity works. Gravity as we understood it couldn't push, it only pulls. And yet the anomaly in our motion persisted, a constant nagging reminder that our cosmic map was still missing a major feature. The clue to solving this profound mystery was hiding in plain sight, imprinted on the very canvas we were using as our reference point, the cosmic microwave background radiation. When we look at this ancient light, it is astonishingly uniform, but not perfectly so. There is a slight variation across the sky, a pattern known as a dipole. One half of the sky is infinitesimally hotter, its light blue shifted. The other half is infinitesimally colder, its light red shifted. This dipole is the definitive signature of our motion through the cosmos. We are moving toward the blue hot pole and away from the red cold one. For decades we assumed the blue pole simply pointed toward the Great Attractor. It was the direction of the pull, but the revelation came when scientists reframed the question. What if the red pole, the direction we are moving away from, was not just a passive receding point but an active source? What if the most important feature on our cosmic map was not a concentration of matter, but a profound and influential absence? This investigation would lead a team of astronomers to a groundbreaking discovery: the confirmation of a structure whose very existence redefines the forces that shape our corner of the universe. They found a vast, previously unidentified supervoid, a region of space so empty, so devoid of matter that its lack of gravity effectively creates an outward push, a gravitational hill that our galaxy and its neighbours are sliding away from. It is an invisible hand, a force born from nothingness that has been shaping our galaxy's destiny for billions of years. This documentary is the story of that discovery. It is the story of the cosmic anomaly that stumped astronomers for a generation. And it is the story of the majestic, counterintuitive and utterly transformative structure now known as the Dipole Repeller. Join us as we venture into the great voids to uncover the unseen architecture of the cosmos and reveal the true, complex and astonishing story of our journey through the stars. You are at this very moment hurtling through the cosmos. The seat you're in, the ground beneath your feet, the very air you breathe, all of it is a passenger on a planetary vehicle, travelling at a speed that defies all human intuition. Forget the gentle rotation of the Earth, a mere 1,000 miles per hour at the equator. Forget its stately orbital waltz around the Sun at 67,000 miles per hour. Those are local movements, familiar and almost comforting in their predictability. We're talking about a speed of a different order entirely. A velocity so immense it must be measured not in miles per hour, but in kilometers per second. Our entire galaxy, the Milky Way, with its hundreds of billions of stars, its spiral arms, a pinwheel of fire and dust, is careening through intergalactic space at an astonishing 600 kilometers per second. That is over 1.3 million miles per hour. An arrow shot across the void. The question that has haunted astronomers for decades is not just how fast we are moving, but the far more profound and unsettling question: what in the vast emptiness of the universe is pushing us, and where are we going? To even begin to grasp the scale of this motion, we must first rewind the cosmic clock, back to a time when our universe was thought to be a placid, static and eternal stage, a grand, silent clockwork unchanging in its overall structure since the dawn of time. This was the prevailing view in the early 20th century, an idea of cosmic permanence that was as elegant as it was comforting. But in the 1920s, from a remote mountaintop in California, the astronomer Edwin Hubble began systematically dismantling that comfortable reality piece by painstaking piece. Using the colossal 100-inch Hooker telescope at the Mount Wilson Observatory, a technological marvel of its day, Hubble was engaged in a seemingly simple task measuring the distances to the faint, fuzzy smudges of light, then known as spiral nebulae. For years, a great debate had raged. Were these nebulae small clouds of gas within our own Milky Way, or were they, as some suspected, entire island universes, galaxies in their own right, lying at unimaginable distances? Hubble found the key to unlock this mystery in a special type of pulsating star known as a Cepheid variable. These stars are cosmic lighthouses. Their intrinsic brightness is directly linked to the rhythm of their pulsation. By measuring how fast one of these stars brightens and dims, you can calculate how bright it truly is. And once you know its true brightness, you can compare that to how dim it appears from Earth, and with that calculate its distance with astonishing precision. When Hubble aimed his telescope at the Andromeda Nebula, he found a Cepheid variable. His calculations were staggering. Andromeda was not a nearby cloud. It was nearly 1 million light-years away, a colossal city of stars entirely separate from our own. The universe in an instant became terrifyingly vast. Our Milky Way was not the entirety of creation, but just one galaxy among countless others. Yet this was only the first of Hubble's revelations, a prelude to an even more world-shattering discovery. For he was not just measuring distance, he was also analysing the light from these newfound galaxies. He did this using a technique called spectroscopy, breaking the starlight into its constituent colours, a rainbow barcode of the elements within. And in these barcodes he noticed something profoundly strange. The specific spectral lines, unique fingerprints of elements like hydrogen and calcium, were not where they were supposed to be. In nearly every galaxy he observed these lines were shifted towards the red end of the spectrum. This phenomenon known as redshift was well understood. It was a cosmic Doppler effect. Just as the siren of an ambulance sounds lower in pitch as it moves away from you, the light from a galaxy moving away from us is stretched, its wavelength elongated, making it appear redder. What Hubble found was not just that some galaxies were moving away, but that almost all of them were. And more than that, he uncovered a stunning, undeniable relationship. The farther away a galaxy was, the faster it was receding from us. The connection was linear, a simple, elegant rule governing the entire cosmos. This was the discovery that tore the static universe apart. The universe was not a fixed and eternal stage, it was expanding. The very fabric of space-time itself was stretching, carrying these galaxies along with it for the ride. This universal expansion became known as the Hubble flow, a majestic, orderly and predictable current in the river of space-time. Imagine a vast, unbaked loaf of raisin bread. As the dough rises in the oven, it expands uniformly in all directions. From the perspective of any single raisin, all the other raisins appear to be moving away from it. A nearby raisin moves away slowly, while a raisin on the far side of the loaf, carried by a greater amount of expanding dough, recedes much more quickly. There is no centre to this expansion within the dough itself. The expansion is happening everywhere at once. This is our universe. We are living inside that loaf. The Hubble flow is the smooth, uniform expansion of the dough of space-time, carrying every galaxy away from every other. It is the baseline rhythm of the cosmos, the great exodus that began with the Big Bang. For decades, this elegant picture seemed to explain the grand motions of the universe perfectly. Galaxies adrift on the currents of space-time were simply following this cosmic tide. We could measure a galaxy's redshift, calculate its speed of recession, and from that infer its distance. It was a beautiful, tidy model. It suggested a universe whose primary dynamic was one of separation, a majestic and lonely dispersal of matter and energy into an ever-expanding future. But nature is rarely so simple, and as our instruments grew more sensitive, as our maps of the cosmos became more detailed, astronomers began to detect faint but persistent anomalies. They found whispers in the data, subtle deviations from the perfect uniform flow that Hubble had first described. The cosmic river, it turned out, was not flowing smoothly. It had currents, eddies, and local rapids. Galaxies were not just passive passengers on the expanding river of space-time. They had their own motions independent of the overall flow. They were swimming in the current. This motion, separate from the Hubble expansion, is called peculiar velocity. It is the subtle extra speed and direction a galaxy possesses due to the gravitational influence of its neighbours. While the universe as a whole is expanding on smaller, more local scales, the persistent tug of gravity is fighting back. Gravity is the great architect of cosmic structure. It pulls matter together, forging stars from gas, gathering stars into galaxies, and marshalling galaxies into colossal groups and clusters. This gravitational pull can be powerful enough to locally overcome the Hubble expansion. The Andromeda Galaxy, our closest major galactic neighbour, is a perfect example. Despite the expansion of space, Andromeda is not receding from us. In fact, its light is blue-shifted. It is hurtling towards the Milky Way at 250,000 miles per hour, drawn by our mutual gravitational embrace. We are destined for a titanic collision, a cosmic merger in about 4.5 billion years. This is peculiar velocity in action, a local gravitational bond defying the universal expansion. Andromeda's approach was a known exception, a local affair. But as astronomers began to survey the sky with greater precision in the 1970s and 80s, they realised that our own Milky Way had a significant peculiar velocity as well. And it wasn't just us. Our entire collection of neighbouring galaxies, a gravitationally bound family we call the local group, was moving in unison. We were all part of a single coherent flow, a stream within the greater cosmic river, and we were all heading in the same direction towards the constellation Centaurus at that incredible speed of over 1 million miles per hour. The Hubble flow could not account for this. The expansion of the universe should be carrying galaxies away from each other uniformly. This synchronized high-speed movement was something else entirely. It was a clear sign that something massive, something with an immense gravitational authority lay hidden just over our cosmic horizon, pulling us towards it with an invisible tether. The great cosmic detective story had begun, and the first clue was our own inexplicable speed. The search for the source of this pull began in our own backyard. Astronomers knew that galaxies are not distributed randomly throughout space. They are woven into a vast luminous tapestry known as the cosmic web. This web consists of dense knotted clusters of galaxies connected by long thread-like filaments, all surrounding vast, nearly empty voids. Our local group is just a tiny suburban outpost on the edge of a much larger galactic metropolis, the Virgo Supercluster. This immense structure, centered some 54 million light-years away, contains over 1,000 galaxies, all anchored by the gravitational heart of the Virgo cluster, a monstrous collection of galaxies including the giant elliptical galaxy Messier 87. For a time, it seemed like a plausible culprit. The combined mass of the Virgo cluster was enormous. Surely this was the gravitational anchor responsible for our motion. We were simply falling towards the centre of our own supercluster, a predictable consequence of living in a dense, gravitationally active neighbourhood. The calculations were made. The mass of the Virgo cluster was estimated, its gravitational influence on us was computed, and the numbers didn't add up. Virgo's pull could account for a portion of our peculiar velocity, a significant chunk, but not all of it. Even after subtracting the gravitational tug of the Virgo cluster, the Milky Way and its neighbours were still left with a massive unexplained velocity, a residual motion still pointing in the same general direction. There was another player on the field, a hidden heavyweight, whose gravitational influence dwarfed even that of the Virgo cluster. The hunt was on for a Great Attractor, a term coined by astronomer Alan Dressler to describe this mysterious source of gravitational pull. The challenge was immense. The direction of our motion pointed towards a region of the sky notoriously difficult to observe. It lay directly behind the plane of our own Milky Way galaxy, an area astronomers call the zone of avoidance. Our view was obscured by a thick curtain of stars, gas and dust from our own galactic disk, making it nearly impossible to see the distant galaxies that might lie beyond. It was like trying to spot a ship on the horizon while looking directly through the sails and rigging of your own vessel. But astronomers are ingenious. They found ways to peer through the smog, using radio telescopes which can detect the long wavelength emissions from hydrogen gas that penetrate the dust, and infrared telescopes which can capture the heat signatures of stars obscured at visible wavelengths. They began to map this hidden region of space. A team of 7 astronomers, who came to be known as the 7 Samurai, embarked on a monumental survey in the late 1980s. They meticulously measured the distances and peculiar velocities of hundreds of elliptical galaxies in every direction, building a 3-dimensional map of galactic motions in our cosmic vicinity. Their findings were revolutionary. They confirmed that the flow was real, coherent, and even larger than previously suspected. They saw galaxies for hundreds of millions of light-years in all directions, all streaming towards the same focal point. Their data painted a picture of a vast basin of attraction, a gravitational vortex in space-time. At its centre, shrouded behind the Milky Way's disk in the direction of the Norma cluster, lay the predicted source, the Great Attractor. They calculated that it must possess the mass of tens of thousands of Milky Way galaxies, a super concentration of matter on a scale previously unimagined. It was a gravitational monster warping the very fabric of space-time around it, compelling everything within a volume of space hundreds of millions of light-years across to fall towards it. We were not just being pulled by Virgo, we were on a much longer, faster journey towards this unseen mass. The discovery was a triumph, seemingly solving the puzzle of our peculiar motion. The universe, it seemed, was a place governed by gravity's irresistible call. Matter clumped together, and these massive clumps pulled in everything around them. It was a simple, intuitive, pull-only model of cosmic dynamics. The Great Attractor was the ultimate gravitational anchor in our corner of the universe. And yet, even as this paradigm was solidifying, unsettling questions remained. Later, more detailed surveys using X-ray telescopes, which can spot the hot gas that pools in the centres of galaxy clusters, did indeed find a large supercluster, the Norma cluster, lurking at the heart of the Great Attractor region. But when its mass was calculated, a familiar problem arose. It was massive, certainly, but it still wasn't massive enough. The Norma cluster and its surrounding structures could only account for a fraction of the gravitational pull needed to generate the colossal velocity we observe. The Great Attractor was real, but it wasn't great enough. It was like discovering a single engine on a ship that was moving with the power of 10. The numbers were still wrong. The mystery, far from being solved, had only deepened. We had found the first culprit, but it was clear that it did not act alone. Something else was at work. Our understanding of cosmic motion was still incomplete. We had accounted for the pull, the obvious force of attraction that draws things together. But we had failed to consider a far more counterintuitive and powerful force shaping our cosmic destiny, a force not of attraction, but of repulsion. The real story of our journey through the universe was not just about what we are being pulled towards, but also, and far more profoundly, what we are being pushed away from. And so, the culprit had a name: the Great Attractor. This unseen titan, a gravitational behemoth lurking behind the dust and stars of our own galaxy, seemed to provide a beautifully complete answer to a question that had haunted us for decades. We were not adrift. We were falling part of an immense celestial river flowing towards a single dominant destination. The case for a time felt closed. Science, however, is rarely satisfied with the first elegant answer. It is a restless, insatiable discipline constantly building new eyes to peer deeper, to question the very foundations of its own triumphant conclusions. As the 20th century bled into the 21st, a revolution in cosmic cartography was quietly unfolding across the mountaintops and deserts of our world. The painstaking work of mapping the heavens galaxy by galaxy was entering a new age of breathtaking efficiency. No longer were astronomers limited to analysing a few hundred cosmic neighbours. Vast automated surveys instruments of exquisite sensitivity began to drink in the light from the deep universe, night after night, year after year. The Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey and others like them were not just taking pictures, they were conducting an unprecedented cosmic census. For tens of thousands, then hundreds of thousands of galaxies, they measured not just their position on the flat plane of the sky, but also their redshift, the subtle stretching of their light caused by the expansion of the universe. This single measurement was the key that unlocked the third dimension. It gave us depth, transforming our flat star-spangled map into a true three-dimensional model of the cosmos. For the first time, we could plot the precise location of entire superclusters and trace the gossamer filaments of the cosmic web that connect them. We were no longer just observers of a grand celestial spectacle. We were becoming its architects, its map makers. With this new fantastically detailed map, the first order of business was to re-examine our own motion, to confirm the powerful, inexorable pull of the Great Attractor with a new level of precision. The expectation was simple, a matter of gravitational elegance. If you plot the velocity of every galaxy in our cosmic neighbourhood, you should see a grand, coherent flow, a sweeping pattern of movement. Every vector, every arrow representing a galaxy's motion relative to the cosmic background should, after accounting for the universe's overall expansion point in a single prevailing direction, they should all converge like iron filings surrounding a colossal invisible magnet on that one dense region in the direction of the Centaurus constellation. The initial data seemed to bear this out beautifully. The dominant flow was undeniable. Our local group of galaxies, the Virgo Supercluster, the Hydra Centaurus Supercluster, all were indeed caught in this mighty gravitational tide streaming towards the Great Attractor. The model held, the theory was sound, but as the maps grew, as the data points swelled from thousands to tens of thousands, a strange and unsettling whisper emerged from the noise. It was a subtle discord in the cosmic symphony, a detail so minor it was at first dismissed as instrumental error, a statistical ghost in the machine. Scientists by their very nature are trained skeptics, especially of their own data. They checked their calibrations, they reran their models, they scrutinized the complex chains of inference that turned faint starlight into a precise velocity vector. The anomaly, however, refused to vanish. In fact, with every new galaxy added to the plot, it grew stronger. It became clearer, more defined, evolving from a whisper to a persistent, undeniable hum. The problem was most apparent when they looked behind us in the direction opposite to the Great Attractor. According to the simple model, galaxies in that region should still feel the distant but powerful pull. They should be moving towards us on their own journey to the Great Attractor, albeit more slowly than we are as they are further away from the destination. We should be pulling away from them, creating an apparent motion of them falling behind. But that is not what the new maps were showing. Instead of a simple uniform flow, the data revealed something profoundly strange, something that seemed to make no gravitational sense at all. It was a divergence, a parting of the ways. Imagine a powerful river rushing towards a great waterfall. Every drop of water, every piece of debris is pulled in the same direction. Now imagine that in one section of that river, an unseen powerful spring is bubbling up from the riverbed. The water directly above it would be pushed upwards and outwards. The current downstream would continue towards the falls, perhaps even accelerated. But the current immediately upstream would be slowed, and the water on either side would be pushed away, creating a visible area of slower diverging flow amidst the powerful unified current. This is what astronomers began to see in the motions of galaxies. In a vast region of space on the far side of the Milky Way from the Great Attractor, galaxies were not just falling towards the attractor, they were also streaming away from a common central area. There was a backflow, an organised large-scale exodus from a specific location in the sky. It was as if the cosmic river, for no apparent reason, was splitting in two. This observation was more than just a puzzle. It was a direct challenge to our understanding of cosmic dynamics. Gravity, the engine of the universe as described by Einstein, is a force of attraction. Mass pulls on mass. It gathers, it clumps, it accretes. It does not on any scale we had ever observed push things apart. The idea of a large-scale repulsive force was alien, a concept relegated to speculative science fiction, not something one finds in the rigorous peer-reviewed data of galactic surveys. The scientific community was thrown into a state of profound quandary. What could possibly be the source of this celestial push? The initial theories were attempts to save the existing model. Perhaps the mass of the Great Attractor had been miscalculated. Maybe it was far larger than we imagined, and its gravitational field was warping space-time in some complex, unforeseen way. Or perhaps there was yet another, even larger attractor located far beyond the first one, whose competing pull was creating this strange divergent pattern in our local neighbourhood. But as the maps became ever more complete, these explanations began to wear thin. The backflow was too coherent, too localized. It wasn't the messy result of multiple competing attractors. It truly looked like a single unified motion away from a specific point. The data was forcing them towards a radical and uncomfortable conclusion. Our motion through the universe was not a simple fall. It was governed by a cosmic dipole, a push and a pull. On one side of us lay the immense gravitational weight of the Great Attractor pulling us forward, and on the other there was something else, something that was giving us a shove from behind. To understand this, scientists had to completely re-evaluate not just the densest parts of the universe, but also the emptiest. For nearly a century we had focused our attention on the bright stuff, the galaxies, the clusters, the great walls of the cosmic web where matter had congregated. But the universe is mostly not that. In between the filaments and clusters lie voids, unfathomable expanses of near-total emptiness regions. where the cosmic web has been stretched thin, leaving behind deserts of dark matter and scattered lonely galaxies. These voids are the largest structures in the entire universe, vast bubbles of nothingness, hundreds of millions of light years across. And it was here, in the absence of things, that the explanation for the mysterious push began to take shape. The push of a void is not a new exotic anti-gravity force. It is in fact gravity itself acting in a way that is subtle and deeply counterintuitive. Imagine you're a small boat floating on a perfectly calm lake. If a massive island, a supercluster, is nearby, you will be gently pulled towards its shore by its gravity. Now imagine that on the opposite side of you a giant sinkhole suddenly opens in the lake bed, a void. The water that was supporting you from that side rushes away into the hole. The result? You're no longer balanced. The pressure from the water on the island side is now greater than the pressure from the sinkhole side. You will be pushed away from the sinkhole and towards the island. It will feel like a repulsive force from the void, but it is actually the result of the unopposed attractive force from everything else. The void does not actively push you. It simply fails to pull on you as much as the rest of the universe does. The push is a consequence of a lesser pull. This was the paradigm shift. The emptiness of space was not passive. It was an active and crucial player in the cosmic dance. The great voids, by virtue of their profound underdensity, exert a kind of gravitational pressure on their surroundings, sculpting the flow of galaxies, herding them towards the dense filaments of the cosmic web. The mysterious backflow, the divergence of galaxies behind us, was the signature of one such colossal void, a vast region of cosmic underdensity. Galaxies on the edge of this void are being pulled away from its empty centre by the denser universe on their other side. Our Milky Way, it turned out, was in a truly remarkable position. We are caught in a cosmic tide, a perfect confluence of these two titanic forces. In front of us, the immense mass of the Laniakea Supercluster, with the Great Attractor at its heart, pulls us relentlessly forward. And behind us, the gravitational influence of an enormous unseen void effectively pushes us onward, accelerating our journey through intergalactic space. Our peculiar velocity of 630 kilometers per second was not the result of a single influence, but the net result of a gravitational tug-of-war played out on a scale of 500 million light-years. The quandary had transformed. The anomaly in the data now had a powerful physical explanation. But with this revelation came a new, even more tantalizing quest. The data didn't just suggest the existence of a void. Its precision allowed us to triangulate its position. The backflow wasn't random. It was diverging from a specific calculable center point in the cosmos. For the first time, we had the tools to not only infer the existence of this immense structure, but to pinpoint it on our celestial maps. We could give a name to the ghost in the machine. The hunt was on not for a great attractor, but for its opposite, a great repeller, the invisible force at our back, the source of the push that has shaped the fate and trajectory of our galaxy since its birth. And yet the numbers refuse to align. For all the titanic gravitational might of the Great Attractor, for all the undeniable influence of the even more massive Shapley Supercluster, looming beyond it, the equation of our cosmic motion remained stubbornly incomplete. Our Milky Way was indeed being pulled, yanked across the expanding fabric of space-time by these colossal structures. But when astronomers subtracted that pull from our observed velocity, a significant phantom motion remained. It was a discrepancy not of rounding errors or instrumental drift, but a fundamental mismatch in the cosmic ledger, a ghostly acceleration that had no apparent source. We were moving faster than we should, a deviation too precise to be random, too persistent to be ignored. This unaccounted for velocity, this vector pointing askew from the great gravitational anchors we had so painstakingly identified, suggested a profound and unsettling possibility. It hinted that we had only been reading one side of the story, that we were witnessing the effects of a force. We couldn't see a dynamic that was not written in the familiar language of gravitational attraction alone. The mystery of our celestial journey, far from being solved, had only deepened, pointing toward an invisible actor playing a decisive role on the cosmic stage. The search for this missing piece demanded a new kind of map, one not just of position but of motion. It required a grand census, a domesday book of the local universe chronicling not just where galaxies were but where they were going. This monumental task fell to international collaborations of astronomers, brilliant and tenacious cosmic cartographers, armed with telescopes that were in essence galactic speed guns. Foremost among them was the Cosmic Flows Project, an ambitious endeavour led by minds like Hélène Courtois, Yehuda Hoffman, and Brent Tully. Their goal was audacious to meticulously measure the peculiar velocities of thousands upon thousands of galaxies across hundreds of millions of light-years. They were not merely stargazers, they were celestial surveyors triangulating the intricate invisible currents of the cosmos. Each galaxy became a data point, a tiny glowing buoy bobbing on the unseen tides of gravity. Using the subtle shifts in starlight, the redshift that tells of recession, and the faint variations in stellar brightness from objects like supernovae and Cepheid variables that act as standard candles, they could calculate a galaxy's true distance, and from that deduce its motion independent of cosmic expansion. It was an excruciatingly precise and painstakingly slow process of celestial forensics. For years, the data streamed in from observatories perched on remote mountaintops, a torrent of photons carrying whispers of galactic drift from the depths of intergalactic space. Each measurement was a single brushstroke in a masterpiece that no one could yet see in its entirety. This was not a picture that could be assembled by eye or by hand. The sheer volume of information was overwhelming a library of cosmic motion so vast it defied conventional analysis. Here the telescope dish gave way to the silicon chip. The raw observations were fed into supercomputers, which began the gargantuan task of constructing a dynamic three-dimensional model of our cosmic neighbourhood. This was not a static star chart. It was a living, breathing digital universe, a simulacrum of space-time where the intricate dance of galaxies could be visualized and understood. Within these computational ecosystems, scientists could finally connect the dots, transforming a seemingly chaotic blizzard of individual galactic velocities into a coherent picture of large-scale flow. They could for the first time see the gravitational riverbeds and watersheds that govern the movement of everything around us. On computer screens in Paris, Jerusalem, and Hawaii, the new map of the universe began to take shape. It was a vision of breathtaking complexity and beauty. The data visualization showed shimmering filaments of galaxies, great luminous rivers of matter, all flowing inexorably toward the dense basins of the Great Attractor and the Shapley Supercluster. The pull was undeniable, a powerful and dominant current in the cosmic ocean. But as the models grew more refined, incorporating more and more data points, something else began to resolve from the digital noise. It was a pattern that was defined not by its presence, but by its absence. As the researchers instructed the computers to trace the flow lines, the paths a galaxy would take over eons, they saw that the motion was not a simple direct line toward the Great Attractors. There was a bend in the river. Our local group, and indeed thousands of galaxies around us, were not just being pulled forward, they were also being pushed from behind. The flow line swerved, peeling away from a particular direction in the sky as if avoiding something. This was the aha moment, a collective, electrifying instant of revelation that would echo through the halls of cosmology. The push was real. It wasn't a measurement error or a computational artifact. It was a fundamental feature of our cosmic environment. The computers traced this repulsive influence back to its source, and what they found was not another gargantuan supercluster of galaxies. It was the exact opposite. The source of this powerful push was an immense, previously uncharted region of space almost entirely devoid of galaxies. A void, a colossal bubble of near nothingness, a profound emptiness, hundreds of millions of light-years across a vast dead zone on the cosmic map. Galaxies on its periphery were not being drawn into it. They were streaming away from it as if fleeing a gravitational desert. The physics was suddenly beautifully clear. In the cosmic web, density pulls and underdensity, the absence of mass effectively pushes. A void exerts a kind of anti-gravity, not because it contains some exotic repulsive substance, but because the gravitational pull from the denser regions on all other sides is stronger, creating a net force away from the empty heart of the void. It's like a cork in water. It doesn't possess a magical rising force, but the pressure of the surrounding water pushes it upward. The team had found the gravitational ghost that had been haunting their equations for decades. They had discovered the invisible hand shoving the Milky Way from behind, adding its force to the pull from ahead. This elegant cosmic push-pull dynamic, this dipole of force, finally balanced the books. The observed velocity of our galaxy, once a baffling anomaly, now made perfect sense. It was the result of a gravitational tug-of-war between the immense mass of the Shapley Supercluster in one direction and the profound emptiness of this newfound void in the other. They needed a name for this crucial newly discovered feature of our universe, a name that would capture its character and its function. They called it the Dipole Repeller. The name was perfect. Dipole because it represented one end of the primary axis of force acting on our local group, the other end being the attractor. Repeller because from our perspective, its effect was to push us away, to shepherd us along our trajectory toward the Great Attractor. The discovery was announced to the world, and with it our understanding of our place in the universe shifted on its axis. The identification of the Dipole Repeller was more than just solving a local kinematic puzzle. It was a profound paradigm shift. It revealed that our journey through the cosmos is not governed solely by the bright shining beacons of galactic superclusters that we can easily see. Our path is equally dictated by the great silent and invisible voids that carve up the cosmic web. Emptiness, it turns out, is not passive. Voids are not just the gaps between the interesting parts of the universe. They are active and powerful shapers of cosmic structure and motion architects of destiny on the grandest scales. The discovery forced us to redraw our maps to see the universe not as a collection of objects in a neutral background, but as a dynamic interplay of density and scarcity of matter and its absence. You're not simply falling toward the light, you're also being swept away from the darkness. The Milky Way's 400 mile per second peculiar velocity is the delicate and precise outcome of this celestial ballet, a dance between a gravitational mountain ahead and a gravitational valley behind. Looking at the new visualizations, you can see it with stunning clarity. You see our local group, a tiny speck poised on the edge of a cosmic watershed. In one direction, the universe is dense, crowded with the glittering cities of the Virgo cluster, the Centaurus cluster, and the distant mountain ranges of Shapley. Gravity there is a powerful summoning force, but if you turn and look in the opposite direction toward the constellation of Eridanus, you're staring into the heart of the repeller. The map here is sparse, a vast expanse of cosmic wilderness, where galaxies are few and far between. It is from this profound emptiness that the gentle but persistent pressure originates a cosmic tailwind that has been accelerating us for billions of years. We now understand that our galaxy resides in a special place, a dynamic interface where the universe's larger structures exert their influence. We live on the slope of a gravitational hill, sliding away from the barren peak of the Dipole Repeller and down into the deep welcoming basin of the Great Attractor and the Laniakea supercluster to which we belong. The discovery gave us a sense of context and narrative that was previously missing. We finally knew the why and the wherefore of our motion. This breakthrough, however, was not an end but a beginning. It opened up entirely new avenues of inquiry, transforming cosmic voids from mere curiosities into objects of intense scientific interest. If a void could be so dynamically significant as to steer the motion of thousands of galaxies, including our own, then understanding their formation and evolution became a top priority. How do such colossal regions of emptiness form in the first place? Are they primordial, born from quantum fluctuations in the crucible of the Big Bang, or do they grow over time as gravity relentlessly pulls matter out of them, evacuating them like cosmic sinkholes? What does the precise shape and scale of the Dipole Repeller tell us about the nature of dark energy? The mysterious force driving the accelerated expansion of the universe, which might find its most potent expression in these desolate expanses. The repeller was no longer just a solution to a problem. It had become a magnificent new puzzle in its own right, a natural laboratory for studying the fundamental forces that govern the cosmos. With this new map in hand, we can now trace our past and project our future with far greater confidence. We can rewind the celestial clock and watch as our local group is nudged out of the expanding void, its trajectory slowly and gracefully bending toward the gathering clans of galaxies that would one day form the Virgo and Centaurus clusters. And we can look forward, seeing our ultimate destiny as we continue our multi-billion-year fall, a journey shaped by both the summons from ahead and the dismissal from behind. The Dipole Repeller provides the missing context, the other half of the cosmic conversation that dictates our fate. It stands as a testament to human ingenuity, a discovery born from the marriage of patient observation and immense computational power. We had peered into the chaos of galactic motions and discerned a hidden order, uncovering a fundamental truth about our universe, that the great cosmic voids are not empty of meaning. They are the silent partners in the grand dance of gravity, and their influence is written into the very motion of our home, the Milky Way. But this profound revelation immediately begs a new, even more daunting question. If our motion is defined by this local arrangement of a supercluster and a void, is this dipole pattern unique, or is it just one small part of an even larger, more incomprehensible structure? How deep does the rabbit hole of cosmic flows truly go? And so we are left staring at a profound cosmic paradox. We have found the source of the push, the great phantom force accelerating us across the universe at over 2 million kilometers per hour. It is the Dipole Repeller, a shadow on the cosmic map. But this discovery presents a maddening contradiction, one that seems to violate the most fundamental law of the cosmos. Gravity, as we have always understood it, only pulls. It is the universe's great gatherer, the force that builds stars, sculpts galaxies, and weaves the cosmic web into existence. It does not push. It does not repel. There is no such thing as anti-gravity in our equations. So how can this be? How can a force that only knows how to attract be responsible for the most significant push our galaxy has ever known? The answer is not found in some new exotic physics, but in a radical shift of perspective, a new way of seeing the universe not as a collection of things, but as a landscape of presence and absence. To understand the push, we must first embark on a journey into the heart of the greatest emptiness we have ever charted. We must learn the anatomy of nothingness. The cosmic web, which we have spent so long mapping, is defined as much by its voids as it is by its filaments. Imagine a delicate three-dimensional lace, intricate and vast. We have always focused on the threads, the glittering chains of galaxies where matter has triumphed, where gravity has won. But for every thread there is a space, a dark volume of quietude. These are the cosmic voids, and they are not small. They are colossal cavernous bubbles of underdensity, some spanning hundreds of millions of light years. The Dipole Repeller is one of these titans of emptiness, but the word void, or empty, is itself a little misleading. These regions are not perfect vacuums in the way we might imagine. They are not sterile voids utterly scrubbed of all matter. Galaxies do exist within them, but they are lonely wanderers, isolated islands in a truly enormous ocean of quiet. If the great superclusters like the one containing the Great Attractor are the universe's bustling, light-saturated metropolises, then the voids are its endless silent deserts. The average density of matter within a supercluster is immense, a riot of stars, gas dust, and the unseen scaffold of dark matter. Inside a void like the Dipole Repeller, the density plummets, falling to less than 1/10 of the cosmic average. There is simply less of everything. Fewer galaxies, less gas, and critically less dark matter. Imagine we could take our own galaxy on an impossible journey, steering the Milky Way directly into the heart of the Dipole Repeller. What would we see? For the first few million years, the change would be subtle, but slowly and perceptibly at first the sky would begin to transform. The familiar neighbouring galaxies, Andromeda and the Magellanic Clouds, would shrink behind us, their light fading into memory. As we plunge deeper, the great rivers of galaxies that form our local sheet would thin out, becoming scattered, distant specks. The universe would grow darker, lonelier. The sky, which from our current vantage point is filled with countless points of light and the faint smudges of distant galactic cousins, would begin to feel barren. Looking out from a planet in a galaxy adrift in the centre of the repeller, the night sky would be an unnerving spectacle of deep, profound blackness, punctuated by only a handful of faint, impossibly distant galaxies. You would feel a sense of isolation that is difficult to even comprehend, a solitude measured not in miles but in megaparsecs. This is the environment that lies behind us. This is the great cosmic quiet from which we are speeding away. But its silence and its emptiness do not explain the push. For that, we must look not into the void itself, but at everything surrounding it. The secret of the push is an illusion, a trick of gravity and geometry. It's a force that isn't really there, yet its effects are undeniable, shaping the fate of 100,000 galaxies, including our own. To unravel this, let's leave the cosmos for a moment and imagine a different kind of landscape, a vast, taut rubber sheet stretched out to represent the fabric of space-time. According to Einstein, gravity is the curvature of this fabric. Heavy objects create dips and wells. A supercluster, like Virgo or the Great Attractor, is a massive weight creating a deep, steep-sided gravitational well in the sheet. A marble placed nearby representing our galaxy will naturally roll downhill into that well. This is attraction. Simple, intuitive. Now, what is a void in this analogy? A void is the opposite. It is a region with far less mass than average. It doesn't create a well. Instead, it is equivalent to a vast, gently sloping hill or a broad plateau on the rubber sheet. Now place your marble, our Milky Way, near the edge of this cosmic hill. What happens? There is no force at the peak of the hill actively shoving the marble away. There is no anti-gravity pushing it. Instead, the marble simply rolls away from the high ground of the plateau and towards the deeper valleys, the gravitational wells that surround it. The push from the centre of the hill is an illusion. The reality is the pull of everything else. The marble's motion is governed by the overall topography of the landscape, the interplay of all the hills and all the valleys. It naturally seeks the lowest ground. Now let us translate this back to the grand arena of the cosmos. The Dipole Repeller is a region of lower mass and therefore lower gravity. It is a gravitational hill in the fabric of space-time. We, the Milky Way and our neighbours, are not being propelled from behind by some mysterious repulsive energy emanating from its core. Instead, the immense galaxy-rich superclusters that lie on the far side of us, like the Shapley Supercluster, the most massive concentration in our local universe, are pulling on us. The Great Attractor is pulling on us. The Virgo cluster is pulling on us. Countless filaments of dark matter and galaxies are all tugging at us. Simultaneously, the vast underdense region of the Dipole Repeller behind us is also pulling on us because it still contains some matter. But its pull is feeble. It is anemic, a whisper compared to the chorus of gravity calling to us from the other direction. Imagine you are the centre of a cosmic tug-of-war. On one side you have a team of titans, massive and powerful. On the other you have a single weak opponent. The rope will inevitably move in the direction of the stronger team. You're not being pushed by the weaker one. You're simply being outpulled by the stronger one. This is the essence of the Dipole Repeller's influence. The net gravitational force on our galaxy is the sum of all pulls from all directions. Because there is a colossal deficit of matter behind us, the pulls from in front of us win the contest, and they win decisively. The result is a powerful acceleration away from the region of gravitational lack. A push born entirely from a universe of pull, it is one of the most elegant and counterintuitive truths in modern cosmology, a solution that required astronomers to stop looking for a new force and start looking at the empty spaces with the same importance as the full ones. With this new understanding, the chaotic picture of our local cosmic motion snaps into stunning focus. For decades, the Great Attractor was the prime suspect for our tremendous velocity. We knew we were moving in its general direction, so it seemed a simple case of gravitational attraction. But the numbers never quite added up. The visible matter in the Great Attractor region, and even the inferred dark matter, was not enough to account for the full blistering speed of our journey. There was a missing component to the equation, a ghost in the machine. The Dipole Repeller is that missing piece. Our trajectory is not a simple beeline towards a single destination. It is a far more complex and beautiful choreography, a gravitational waltz between two opposing yet complementary partners. Picture our local group of galaxies as a leaf carried on a cosmic river. Far downstream, a massive waterfall thunders the Great Attractor, its immense gravity pulling the river of space-time towards it. This is the primary destination, the dominant pull defining the river's general course. But the river must begin somewhere. It originates high up on a vast featureless plateau, the Dipole Repeller. The slope of the land itself, the gradient from the high plateau, down to the low basin of the waterfall, is what gives the river its speed. The water isn't being pushed from its source. It is flowing along the path of least resistance down the gravitational gradient. Our motion is a delicate balance of these two titanic influences. The Great Attractor defines the primary where of our journey. The Dipole Repeller, by creating a steep gravitational slope behind us, is the critical factor in defining the how fast. It effectively clears a path, creating a cosmic downslope that allows the pull of the Great Attractor and other distant structures to be even more effective. It is the starting gun and the tailwind for our galactic race across the cosmos. Without the repeller, we would still be moving towards the Great Attractor, but far more slowly. Our observed velocity would remain a deep mystery. With it, our motion makes perfect, elegant sense. We are being pulled from the front and pushed from behind a push, created by an absence of pull. This revelation does more than just solve a local puzzle about our velocity. It fundamentally redraws our map of the universe and redefines our place within it. For centuries, we have been creatures of the light. We mapped the cosmos by connecting the dots, focusing on the bright concentrations of matter, the stars, the nebulae, the galaxies, the clusters. We saw the universe as a dark void populated by brilliant things. The voids were just the boring passive backdrop, the canvas on which the real masterpiece of creation was painted. This discovery forces us to change that view forever. The voids are not passive. They are not empty stages. They are active, dynamic players in the cosmic evolution. They are the architects of the universe's structure, their subtle, effective repulsion sculpting the flow of matter, herding galaxies into the filaments and walls of the cosmic web. They are the yin to the supercluster's yang, the necessary emptiness that gives shape and meaning to the concentrations of matter. By understanding the Dipole Repeller, we learn to read the entire landscape, to see the universe not as a collection of objects, but as a single, interconnected gravitational entity. We now understand that to know your destination, you must also fully appreciate the nature of the place you're leaving behind. Our cosmic address has suddenly become far more specific. We live on the outskirts of the Virgo Supercluster. We are flowing along the local sheet of galaxies. We are being pulled towards the Great Attractor and the Shapley Supercluster. And we are being pushed from behind by the Dipole Repeller. Every part of that sentence is equally important. It is a story of attraction and repulsion, of density and scarcity, a complete and holistic picture of our place in the flow. We are not merely falling. We are part of a grand cosmic current, a river of galaxies flowing from a gravitational highland towards a gravitational sea. This realization is a profound testament to our relentless curiosity. We have looked out into the darkness between the stars and found not an absence of meaning, but a new and powerful truth, a force hidden in plain sight, written in the geometry of emptiness. We have solved the mystery of our own motion, but in doing so we have uncovered an even larger, more tantalizing map. If our local flow is governed by this dance between an attractor and a repeller, what about the flows of other superclusters? Are these structures, the Dipole Repeller and the Great Attractor, unique players, or are they merely two actors on a much, much larger stage? As we zoom out, does this pattern repeat? Are there even greater voids and more massive attractors out there, dictating the flow of the universe on scales so vast they challenge the very foundations of our cosmological models? Having finally understood our own cosmic neighbourhood, the irresistible temptation now is to look beyond the horizon to see just how deep this cosmic river truly flows. And so, the Dipole Repeller ceases to be just an object or even a place. It transforms into a principle of the universe, a fundamental truth about the relationship between something and nothing. For a century, our cosmic maps were drawn with ink, charting only the islands of light, the continents of matter. We saw the superclusters, the Great Attractors, as gravitational mountains, their peaks, pulling us inexorably forward. But we had only been reading half of the map. To truly understand our journey, our galaxy's 700-mile-per-second pilgrimage, we have to learn to read the blank spaces, to see the architecture hidden within the abyss. We have to zoom out far beyond Laniakea, far beyond Shapley, until our own supercluster becomes just a single knot of light in a structure of almost unimaginable scale. This is the cosmic web. It is the universe's largest and most profound pattern, a ghostly, luminous lacework stretching for billions of light years in every direction. This is not a metaphor. It is the physical, observable skeleton of the cosmos. Imagine flying backward at impossible speeds, the familiar constellations dissolving, the Milky Way shrinking to a pinprick. galaxies, once majestic spirals, become mere motes of dust. Soon, you begin to see the grand design. You see that galaxies are not scattered randomly like seeds thrown to the wind. They are organized. They trace shimmering incandescent filaments across the darkness, rivers of light flowing through the emptiness of space. These filaments, woven from thousands of galaxies and threaded with invisible dark matter, stretch for hundreds of millions of light years, connecting the universe like a colossal nervous system. Where they intersect, where the rivers of galaxies converge, you find the great hubs of cosmic activity, the superclusters. These are the dazzling, hyperdense metropolises of the universe, nodes of unimaginable mass and energy. Places like the Shapley Supercluster, glowing white-hot with gravitational power. It's here that the universe is most alive, where galactic evolution proceeds at a furious pace, driven by mergers, collisions, and cataclysmic bursts of star formation. But this glittering network, this brilliant filigree of existence, is defined by what it surrounds. Between the filaments lie the voids, vast, dark, and profoundly empty expanses of space, some so large that our entire Laniakea supercluster would be lost within them. These are the cosmic badlands, the great deserts of the universe. Here the density of matter drops to a fraction of the cosmic average. Galaxies are few and far between, lonely stragglers in an ocean of quiet. For decades we saw these voids as passive as simply the gaps between the interesting parts. They were the negative space, the canvas upon which the real story was painted. This was a profound misunderstanding. The cosmic web is not just a story of matter, it is a story of gravity. And gravity is a tale told by both presence and absence. The filaments and clusters are gravitational highlands, cosmic mountain ranges whose immense mass creates deep wells in space-time, pulling everything towards them. The voids in turn are the gravitational valleys. They are not empty pits, but vast, gently sloping plains where the pull of gravity is exceptionally weak. They are regions of cosmic underdensity, places where the universe has been hollowed out. Now return with us to our own cosmic neighbourhood armed with this new universal perspective. Look again at the Dipole Repeller. It is not a mysterious force field pushing us away. It is not some exotic object spewing anti-gravity. The Dipole Repeller is a supervoid. It's a colossal underdense region of the cosmic web, a gravitational valley sprawling directly behind the Milky Way. The push, we feel, is the consequence of its profound emptiness. Think of yourself on a perfectly calm lake held in place by ropes being pulled with equal tension from every direction on the shore. You are stationary, balanced. Now imagine the entire team of people on the shore directly behind you suddenly lets go of their rope. You don't get pushed from behind, you are simply pulled forward by the now unopposed tension of the ropes in front of you. The net force has shifted. This is the elegant and powerful truth of the Dipole Repeller. It isn't an active push, it is a passive release, an architectural feature of the local universe. The great mass of the Shapley Supercluster and other structures ahead of us are pulling on one rope. The vast matter-starved region of the Dipole Repeller behind us has let its rope go slack. Our galaxy, caught in this cosmic tug-of-war, accelerates toward the greater pull. This simple, beautiful concept resolves one of the greatest paradoxes of our motion. The force acting upon us is not a simple attraction to a single point. It is a bulk flow, a current in the river of space-time, and this current is directed by the topography of the entire cosmic watershed. Every galaxy you can see, every cluster we have ever mapped is caught in a similar flow, its motion dictated by the landscape of the web around it. Galaxies flow away from the centres of voids like water draining from a high plateau. They stream along the filaments channeled by these gravitational canals, cascading toward the great basins of the superclusters. Our local group is not on a solitary journey. We are part of a vast coordinated movement of tens of thousands of galaxies, a continental drift on a cosmic scale. The Dipole Repeller is our local valley, and Shapley is our local mountain range. But this dynamic is not unique to us. It is universal. Look anywhere in the cosmos, and you will see the same process at play. The Hercules supercluster is being pulled by the Corona Borealis supercluster, while simultaneously being nudged along by the immense Bootes void, a famously colossal bubble of near-nothingness. Entire sections of the web are in motion, pulled and shaped by even larger concentrations and even more profound voids just over the cosmic horizon. The universe on its grandest scale is a dynamic and interconnected system, a symphony of gravity where the silences, the voids are just as important as the notes. They provide the rhythm, the tension and release that drives the entire composition. Realizing this required a monumental shift in both theory and observation. It is one thing to sketch this idea, another to prove it. The proof comes from two extraordinary fields of human endeavour, the virtual and the real. First, we built new universes inside supercomputers, using our best understanding of physics of gravity, dark matter and dark energy. Scientists created simulations of cosmic evolution on an unprecedented scale. Projects like the Millennium and Illustrious simulations begin with a nearly smooth uniform universe just after the Big Bang, and then let the laws of physics play out over 13.8 billion virtual years. What emerges from the cold logic of these computations is breathtaking. Slowly over eons, tiny fluctuations in density begin to grow. Dark matter, the invisible scaffolding of the cosmos, starts to clump together under its own gravity. It forms a vast interconnected network of filaments. Normal matter, the stuff of stars and galaxies, is then drawn into this web, lighting it up like dew on a spider's silk at dawn. And between these filaments, the voids naturally open up as matter is evacuated from these regions and pulled into the denser structures. The simulations didn't just predict a cosmic web. They built one from first principles that looked astonishingly like the one we observe. They showed with undeniable clarity that voids are not accidental gaps. They are a non-negotiable fundamental consequence of gravitational collapse. You cannot form the glittering superclusters without simultaneously creating the desolate supervoids. They are two sides of the same cosmic coin born together in the early universe. These digital universes became our laboratories, allowing us to see how the push and pull dynamic shapes galactic flows across billions of years, confirming that the interplay we see locally is the standard operating procedure for the entire cosmos. But a simulation, no matter how powerful, is only a model. To truly map our reality, we had to undertake one of the most ambitious projects in the history of astronomy, to survey the sky not just in 2 dimensions but in 3. We needed a map that had depth. Massive undertakings like the Sloan Digital Sky Survey and its successors did exactly that. For decades, telescopes have been systematically capturing the light from millions of galaxies. For each one, they measure its redshift, the stretching of its light caused by the expansion of the universe. This redshift gives us a crucial piece of information: the galaxy's distance. It allows us to place each point of light not just on the sphere of the sky, but at its correct depth in cosmic space. As the data poured in year after year, galaxy by galaxy, the structure emerged from the noise. The abstract idea of a cosmic web solidified into a tangible, intricate map of our universe. We could fly through it. We could trace the filaments, navigate the voids, and pinpoint the superclusters. And on that map, we could plot the observed velocities of galaxies, their peculiar motions, their deviations from the smooth expansion of space. When we did this, the picture became whole. The flows we saw in the real universe, the bulk flows carrying thousands of galaxies, matched the predictions. Galaxies were indeed flowing away from the centres of the great voids we had mapped, and were streaming along the filaments toward the clusters. And there, on our own doorstep, was the final stunning confirmation. The observed motion of the Milky Way, the 700-mile-per-second enigma that had puzzled astronomers since its discovery, could finally be accounted for with breathtaking precision. The model was no longer just about the pull of the Great Attractor, or the even greater pull of the Shapley Supercluster. It was about the holistic influence of the entire local web. It was the sum of all the pulls from the Virgo cluster, the Norma cluster, the Hydra Centaurus supercluster, and the immense Shapley concentration. But it was also crucially the sum of all the absences. It was the lack of pull from the vast empty region of the Dipole Repeller. When you combine all these forces, all the tugs from the gravitational highlands, and all the releases from the gravitational lowlands, the conflict is resolved. The equation balances. Our galaxy's velocity and direction are no longer a mystery. They are the perfectly natural, predictable result of our specific address within this glorious interconnected cosmic structure. We are not being singled out by some strange anomaly. We are simply following the local contours of space-time, drifting on the currents of the web just like everyone else. This revelation marks a coming of age in our understanding of the cosmos. We have moved beyond a universe of objects to a universe of structures. We see now that the largest things in existence are not the clusters, but the voids they outline. We understand that the most powerful shaping force is not just the crushing presence of matter, but also its eloquent and architectural absence. The Dipole Repeller was the key that unlocked this grander view. It forced us to look over our shoulder into the dark, and in doing so, it taught us to see the whole. It showed us that to understand where you're going, you must first appreciate the significance of where you are not. Our place in the universe is now defined as much by the emptiness behind us as it is by the dazzling chains of galaxies that lie ahead. We reside on the slope of a great cosmic valley, participating in a celestial choreography that spans the observable universe. But knowing the pattern raises an even deeper question. This intricate web, this precise balance of matter and void that dictates our fate, where did it come from? What planted the seeds of these structures in the fires of the Big Bang setting? In motion, the 14 billion-year construction project that built the world we now see. And so, the great cosmic chase finds its unexpected conclusion. The phantom that has shadowed our Milky Way for billions of years, the unseen force working in concert with the Great Attractor, is finally brought out of the darkness and into the light. It is not an object, not a colossal concentration of mass, but its perfect opposite, a profound and monumental emptiness. The Dipole Repeller, a name that echoes with a strange poetry, describes not a presence, but a staggering and influential absence. For decades we believed our story was one of pure attraction, a simple tale of being pulled towards an immense gravitational anchor. We now understand the truth is a far more elegant, complex ballet. Our journey across the cosmos is a delicate dance of push and pull, a gravitational tango choreographed by both matter and the void. This revelation does more than simply solve a celestial mystery. It fundamentally reconfigures our place in the universe. It forces us to reconsider the very nature of cosmic architecture, to see the empty spaces not as passive backdrops for the stars, but as active, powerful sculptors of cosmic destiny. To truly grasp the significance of this discovery, we must journey back to the heart of the scientific process itself, for the story of the Dipole Repeller is a testament to humanity's most noble and enduring quality, our relentless curiosity. It began not with a grand vision, but with a persistent anomaly, a subtle nagging imperfection in our portrait of the early universe. The cosmic microwave background radiation, that faint afterglow of the Big Bang, was meant to be almost perfectly uniform, a smooth canvas. Yet it possessed a strange asymmetry, a cosmic dipole, one side of the sky fractionally warmer, the other fractionally cooler. This was the universe whispering a secret, a directional clue, the first breadcrumb on a trail that would lead across billions of light years. For years, this clue was interpreted in the simplest way possible. We were moving, and something enormous was pulling us. The hunt for this great attractor became a multi-generational quest, a search for a hidden titan lurking behind the dusty veil of our own galaxy. But even after its discovery, the numbers never quite added up. The pull of the Great Attractor and even the more distant Shapley Supercluster could not fully account for the tremendous velocity of our local group. There was still a ghost in the machine, an unaccounted for motion. This is where science transcends mere observation and becomes an act of courage. It is the moment a scientist must be willing to question everything, to challenge the foundational assumptions of their own search. What if they were only looking at one side of the equation? What if the answer wasn't just about what was pulling, but also about what might be pushing? This singular question, posed by teams of visionary cosmographers, ignited a revolution in our understanding of the universe. It required the development of new techniques, new ways of seeing. It demanded the painstaking collection of data from thousands of galaxies, each one a tiny flickering data point in a colossal 3D puzzle. Led by figures like Hélène Courtois, Brent Tully and Yehuda Hoffman, these modern-day cartographers embarked on an audacious project to map not the positions of galaxies but their movements. They sought to chart the invisible rivers of gravity, the cosmic currents that shepherd trillions of stars across the eons. Their tools were the world's most powerful telescopes, their language was mathematics, and their canvas was the largest structure in the known universe, the cosmic web. Using the peculiar velocities of galaxies, their motions independent of the universe's overall expansion, they began to build a new kind of map. It was a map of flow of gravitational watersheds and cosmic tides. And as this unprecedented map took shape, the truth began to emerge. They saw the great streams of galaxies flowing towards Shapley as expected. But they also saw something astonishing, something no one had predicted. They saw galaxies on the other side of the sky streaming away from a vast unseen region with equal determination and vigour. It was as if they had discovered a continental divide on a cosmic scale. On one side, everything flowed into the Shapley Basin of Attraction. On the other, everything flowed away as if from a great summit. This summit, this source of the cosmic push, was the Dipole Repeller. The data revealed it to be an immense underdensity, a void so large that its lack of matter creates a gravitational deficit. Imagine the fabric of space-time as a stretched rubber sheet. A supercluster is a heavy bowling ball creating a deep well that things fall into. The Dipole Repeller is the opposite. It is like a huge invisible hand lifting the sheet from underneath, creating a hill. Galaxies like marbles on this sheet naturally roll downhill away from the repeller and towards the deepest wells like Shapley. This elegant, beautiful symmetry completed the picture of our motion. We are not simply falling towards the light. We are also fleeing the dark. Our 630 km per second journey through space is a product of this cosmic balancing act, this gravitational yin and yang. The discovery was a triumph of collaboration of shared data and international effort, a shining example of what we can achieve when we pool our resources to answer the universe's biggest questions. It is a story that reminds us that progress is not always a straight line. Sometimes the greatest leaps forward come from turning around and looking at the problem from the opposite direction. Sometimes the most important thing in the universe is the nothing that is there. The implications of this new understanding are profound, rippling through nearly every aspect of modern cosmology. For generations, we have characterized the universe by its contents, its brilliant stars, its swirling galaxies, its colossal clusters. The spaces in between were largely ignored, dismissed as inert emptiness. The Dipole Repeller forces a radical re-evaluation of this perspective. Voids, these great bubbles of near-nothingness that dominate the cosmic web, are not passive gaps in the tapestry of creation. They are active and essential components of the cosmic engine. They are the counterweights to gravity, the architects of large-scale structure. Their subtle, persistent influence governs the flow of matter-herding galaxies into the filaments and walls of the cosmic web. They are the invisible weather systems of the cosmos' vast high-pressure zones that dictate the direction of cosmic winds. Understanding the repeller means we must now study voids with the same intensity we have reserved for superclusters. We must map their boundaries, measure their depths, and model their influence. They are a new frontier in our exploration of the universe, a dark and silent realm whose secrets are only just beginning to be unveiled. Furthermore, this discovery reshapes our very sense of home, our cosmic address. For so long we defined our location by what we were, a part of the Earth in the solar system, in the Milky Way, in the local group within the Virgo supercluster itself, a small province of Laniakea. Each step was a submission to a larger, more powerful gravitational master. Now we must add a new paradoxical element to that address. We are residents of the Milky Way, a galaxy being actively pushed by the great void that lies behind us in the cosmic rearview mirror. Our galactic neighbourhood is not a quiet suburb. It is a dynamic thoroughfare defined as much by the empty lot across the street as by the luminous metropolis down the road. This dualism, this push and pull, is likely not unique to us. The Dipole Repeller and the Shapley Supercluster form just one dipole, one axis of motion, in a universe filled with them. Cosmologists now believe that the cosmos is likely filled with such structures, countless repellers and attractors, locked in a silent gravitational struggle, each pair working to orchestrate the movement of trillions of galaxies. The cosmic web is not a static scaffold, it is alive. It is a dynamic flowing network, a circulatory system on an unimaginable scale, with voids acting as the hearts that pump rivers of matter through its veins. Our own motion is just one tiny eddy in this incomprehensible cosmic ocean. This new perspective offers us a humbling yet exhilarating view of our existence. We are passengers on a galactic vessel, the Milky Way, and for the first time we understand the currents that guide our voyage. We are being propelled through the intergalactic medium by forces generated over scales that dwarf human comprehension. The source of this push is an entity we can never truly see, whose very nature is defined by an absence of light and matter. It is a gravitational ghost, its presence felt only by its effect on everything around it, including our own spiral home. There is a profound philosophical weight to this realization. Our destiny. The physical path we trace through space-time is shaped by something invisible, something defined by what it is not. It is a cosmic metaphor for the unseen forces that shape our own lives, the subtle influences and hidden structures that guide our choices. It speaks to the limits of our perception, reminding us that the most powerful things in the universe may be those that are inherently invisible to our eyes. We have spent centuries looking up at the lights in the sky, believing they held all the answers. The Dipole Repeller teaches us that we must also learn to look at the darkness, to study the silence, and to appreciate the profound power of the empty stage on which the cosmic drama unfolds. And yet this incredible discovery is not an endpoint. It is not the final chapter in our cosmic story. Rather, it is the opening of a door into a much larger room, revealing a landscape of questions more vast and complex than the ones we have just answered. The search is now on for other similar structures across the universe. Do all superclusters have a corresponding repeller? Is this push-pull dynamic a universal principle of cosmic evolution? Answering these questions requires new eyes on the sky, next-generation surveys that will map the motions of millions of galaxies with unprecedented precision. Observatories like the Vera C. Rubin Observatory and the Euclid Space Telescope are poised to create the most detailed 3D maps of the universe ever conceived. They will not just see the brilliant clusters, but will also delve into the shadows, charting the contours of the great voids and revealing the full dynamic sweep of the cosmic flow. These future explorations will test the very foundations of our cosmological models, the Dipole Repeller. A local phenomenon also serves as a crucial stepping stone towards understanding the greatest mystery of all dark energy. On the grandest of scales, the entire universe is expanding at an accelerating rate. Some unknown repulsive force is pushing everything apart, overwhelming the collective gravity of all the matter in the cosmos. This force, which we have named dark energy, behaves like a universal repeller. Could the voids like our dipole repeller be the key to understanding it? Are they localized pockets where the influence of dark energy is more pronounced? Or is their repulsive nature a pure consequence of gravity and mass deficit, a simple mechanical process that only mimics the deeper mystery? By studying the Dipole Repeller, our own cosmic backyard engine, we have a tangible local laboratory to investigate the nature of cosmic repulsion. It is a foothold, a place to begin our assault on a question that strikes at the heart of reality and the ultimate fate of the universe. The quest that began with a faint anomaly in the light of creation has led us to the edge of an even greater darkness, a frontier of knowledge that promises to redefine physics itself. So when you look up at the night sky, at the serene and silent stars, remember the unseen drama unfolding around you. Remember that you are on a journey, a passenger on a starship of immense proportions, travelling at over 2 million kilometers per hour. You're being pulled towards distant, glittering islands of light, and you're being pushed by a vast, invisible ocean of emptiness. You're part of a cosmic dance that began 13.8 billion years ago, a dance of gravity and voids of matter and its absence. The discovery of the Dipole Repeller is a monument to the human spirit, a declaration that no mystery is too vast, no force too subtle to escape our relentless quest for understanding. It reminds us that we are not merely passive observers of the cosmos, but active participants capable of mapping its hidden geographies and deciphering the laws that govern its majestic evolution. The universe is a book filled with endless pages, and we have only just learned how to read the spaces between the words. Our journey, like that of our galaxy, is defined not only by the brilliant things we are drawn towards, but by the great and silent emptiness from which we are propelled ever forward into the heart of the next mystery.